Alright, so we have a projectile that's been launched at the A, that's the zenith, which is the maximum height, and you're told its velocity is 8 meters per second, so that's a nice hint of a way of saying that the horizontal velocity is equal to 8 meters per second, however vertical velocity there is 0. Acceleration due to gravity is 10, always use what's given in the question. So, and B is 0.6 seconds later. On the diagram, show an arrow the direction of velocity of the projectile at point A. So there it's just straight horizontal velocity. Calculate magnitudes of vertical and horizontal components at projectile point B. Well, we don't need to work out the 8 meters per second there because horizontal velocity is constant throughout the projectile motion path. However, it starts from 0 here and falls down to B, so V vertical velocity is equal to initial vertical velocity plus a half AT. Initial velocity is 0, substitute your other values, grab a calculator, and you end up with 1.8. Calculate the magnitude of the velocity. So always draw your vector diagram. So we have the horizontal velocity, vertical velocity, grab Pythagoras, substitute your values and work out your answer. Now it only said the magnitude, however I did the extra calculation for the angle, so tan theta, opposite over adjacent, substitute your values, rearrange, grab a calculator and you work out the angle. All right. So we've got a projectile that's been launched, so the first thing you can do is going to work out your vertical velocity and your horizontal velocities. I drew it up there because I couldn't really fit it in this gap here. Makes no difference. So sine is actually the opposite one, that's your vertical velocity. So that's going to be the vertical velocity divided by the hypotenuse, which is 30. Substitute your values, rearrange, grab a calculator. Likewise, cos, the horizontal velocity is adjacent to the angle. Use the cos function. Substitute your values, rearrange, grab a calculator. Now the projectile is going to be launched from a height. Describe and explain launching from the height has on the range of the projectile in comparison to its launching from the ground. Alright, so the time of flight is going to be increased because you're actually lifting it higher. So therefore the range is going to increase. Also the angle which it collides with the ground is going to be larger because that vertical velocity here is going to be larger because it actually falls an additional height here. So therefore that angle which is alternate there would also increase. Alright, so in this question here we've got the multi-image diagram of the ball being showing that parabolic path. The time interval between here is actually 1 second. Alright, so calculate the horizontal speed of the projectile. Now you could simply just do 10 divided by 1. However, that wouldn't be best practice to average over the whole lot. You'd do 40 divided by the intervals, so 1, 2, 3, 4. So then it'd be 40 divided by 4, which gives you 10 meters per second. So that's best practice. What is the maximum height reached by the projectile? So you go back to the diagram and you actually read off the value. Calculate the magnitude and vertical acceleration of the projectile. So what is the initial velocity? So I've got 15 over 1. Where did that come from? So initial velocity was 0. It changed to 15 over a 1 second period. That's the height or a distance. So that velocity here is going to be 15 meters per second. In the next interval, it goes from 15 to 20. So that's a change in 5 meters over 1 second. So the change in velocity here is 5 meters per second. So I've shown the calculations there. So 5 take 15, divide by 1, and that would actually give you 10 meters per second squared. Another way of actually doing it would be to use this equation here, where you would actually look at the motion from the height. So the initial vertical velocity here is equal to 0. It then travels 20 meters. in a period of 2 seconds. So initial velocity is 0, so that drops off. Here's your equation, rearrange, substitute your values. So there's the 20 meter height in a 2 second period, and you end up with the same answer. So both of those would be valid. So we've got a stone that has been thrown horizontally, so there is no vertical velocity. So when that actually starts to fall, the vertical velocity is going to increase due to acceleration. Alright, so draw a vector diagram showing the horizontal and vertical components as it reaches point X. Alright, so we've got the 25 meters there, and we're told that the vertical velocity, so vertical component velocity at that point is 36. So we substitute that into our diagram, and the velocity is the hypotenuse. Grab Pythagoras, substitute, calculate, work out your answer. Now this was not required. However, what is the angle that it hits the ground? So tan of theta is equal to the opposite over adjacent. So 36 over 25. Rearrange, chuck it in the calculator, and always, when you have an angle, always put in the reference point there. Also, as you can see here, there's my theta. However, our reference is the ground or the horizontal. Alternate angles, always put in a mathematical reason if you're going to be doing that sort of stuff. Tennis player hits the ball, so therefore there is no vertical velocity initially, so we're going to be working that out at some stage. And we've got a net 15 meters. Show that the ball takes 0.6 seconds to reach the net. Okay, so we've got 25 meters per second. That's all horizontal velocity. That's not going to be changing. So velocity is equal to distance over time. Rearrange, time is equal to displacement over velocity. Substitute, grab a calculator. All right, so now we're calculating the change in height of the ball during this time. Now it's launched horizontally, so there is no vertical component, so that actually it is 0 and cancels out. Substitute our values, so we're actually told the time to confirm, so we can use that one there. So the displacement, it actually falls as 1.8 meters. Determine the height in which the ball hits the net. Well, it was served from 2.5, it fell 1.8, so therefore it's actually 0.7 meters off the ground. The height of the net's 9, do the subtraction, so that means it's hit 20 centimeters below the top of the net. Again, always good to put a reference. Now the tennis player's aim is to hit the ball so it goes over the net. Really? So how can we change it? So if we actually increase the horizontal velocity, so that means there's going to be less time for it to reach the net, so therefore it's going to drop less input in that time period, so therefore it'll make it in time. Or you could just increase the angle so the time of flight's increased, so therefore it falls from a greater height and it will make it in time to get over the net. Please note this question says 1, so if you actually put in 2 reasons, like I did, then you would actually not be marked on the second part there. However, I'm just explaining both possible options. So now we've got a softball hitting it at 50 degrees, 1 meter off the ground. However, it's going to be landing 1 meters off the ground, so you can just pretend that's uni-level projectile motion. 34 meters per second at 50 degrees. At some stage you'll need to break up the horizontal and vertical components. Calculate the time the ball takes to reach the outfielder, so time, so that's when we are looking at the vertical component. So sine of 50 equals the vertical velocity over the hypotenuse there. We've already done those diagrams several times, so I'm not going to do that again. Right, rearrange, substitute, put in the calculator. What is the change in velocity to work out the time? Divided by the acceleration, substitute, and don't forget, when you get your final answer, you'll need to times it by 2 because you're only working out the time from here to here as opposed to from here to there. All right, so you end up with 5.3 seconds when you round it off to 2 sig figures. Tennis ball is now hit from the same height with same initial velocity as for the softball. All right, 2 balls are shown photograph before. Okay, so what's one difference that the balls describe how affect air resistance. So the tennis ball's fluffy, the softball's smooth, and therefore the tennis ball is going to trap more air, and therefore the air resistance will be higher. The softball is quite smooth, however it is larger, so the surface area has increased. So it's going to collide with more air. Okay, so therefore the softball air resistance will be higher. You'd be marked incorrectly if you chose mass, because mass does not affect air resistance, though it will affect the projectile path, mainly because you're supplying the same force with a heavier object. However, that is a question regarding inertia, so not air resistance. So we've got another projectile here being hit at 16 meters per second, angle 40 degrees. So we're going to break that up into its vertical and horizontal components. So substitute your values here, rearrange, grab a calculator, chuck out the answer. Time of flight is 2.1 seconds. Calculate the range of the projectile. So we need the horizontal velocity in order to get the range. So velocity is distance over time, displacement equals velocity times time. Make sure you put in the horizontal velocity, not the vertical one, very common mistake, and the time period, and you end up with the range. Calculate the vertical components at t equals 2 seconds. So velocity equals initial velocity plus at. Velocity at launch was 10.3. We worked it out over here. Times it by negative 9.8 because it's actually going upwards as opposed to the opposite direction we have here. And we end up with 9.3 meters per second. Now you could do it a more complicated way because you're told that it's 2.1 seconds. So the zenith height to reach the maximum height would be 1.05 seconds. So working out there. So we actually know it's gone over the zenith and it's actually starting to fall down, which is very important, especially if you're trying to do a logical calculation in your head about whether it's negative or positive in terms of its motion. Alright, so what we have here, similar equation there. If we're doing it from the zenith, maximum height, that's going to be equal to 0. What is the time that it's actually fallen? So that was the time it took to get to the middle, the maximum height, and the 2 seconds there. Substitute the values and you get a very similar answer. This would be the more preferred answer, but that one could also be justified. Again, labeled vector diagram. Always stick in your labels there. Calculate the resultant speed, so therefore it doesn't want the angle. So you draw that. So you're working out the total velocity here. Pythagoras, substitute, calculate, and there's your answer. And that's missing meters per second. So we've got another multi-image diagram here. And I've already scribbled on some marks here, but I can already tell that the distance between these is quite uniform, which is what we expect because horizontal velocity is constant. So using this image, show that the projectile did not undergo any horizontal acceleration. Okay, horizontal displacement per unit of time was uniform, so therefore there's no change in velocity. Acceleration is 0. So that's straightforward. Anyone who actually put in measurements and used actual values would be marked incorrect for this one. Alright, so this question hasn't appeared for a while. So you've actually got two paths and they actually meet here. So I've already scribbled on some notes there. Alright, so on the diagram, draw vectors, show the direction and magnitude of acceleration. So they're 9.8 and they're both the same and they're acting downwards. Alright. State the size of angle theta. So this is an old question where the two angles that add up to 90 are the same path. Now I'll just show you this in simulation. So I've got this Excel worksheet that I made years ago. So if I have an angle at 30 degrees and they're both traveling at 5 meters per second there, and I then type in 60 degrees because 30 plus 60 equals 90, you can actually see here and here they actually meet, and they're both acting on the 0 line. Okay. Now, what's actually happening here? Well, the 30-degree one actually has a larger horizontal velocity, but its time of flight is decreased because its vertical velocity is actually quite small. When I've got the 60-degree one, its horizontal velocity is actually quite small. However, it gets to travel further because its vertical velocity, which is affecting its time of flight, is quite large. All right. Now, if I change this to, let's say, 20, then the other angle that would match it would be 70 degrees. Again, you can actually see it crosses over on the 0 on the x-axis here at the same point. 35 and 55, so those both would add up to 90 degrees. You can still see here they cross over. And there is an actual derivation for it, but it's highly complicated and not part of the course anymore. But there is a bit of a proof there. So it's a very old question that they recycled, but all you need to know is that the two angles, when you add them up to 90, will have the same range. Alright, so this question here is the same as the previous one, where the person was actually catching the ball. However, it's in a different scenario. What is the acceleration of the motorcycle at points A, B, and C? Well, it's always 9.8. It's launched with initial velocity of 20.5 meters, 42-degree angle above the horizontal. Time of flight is 2.81 seconds. What is the magnitude of the horizontal component? So again, horizontal, you're always going to go for the cos function, substitute values, grab a calculator, hit the answer, of course they match. Calculate the range where you're going to be using horizontal velocity. You now know the time because the time was actually given here in the original question. So displacement equals velocity times time, substitute and grab a calculator. State whether the motorcycle will be still on ramp 2 if the launch height is decreased. Now we're making the assumption that the bike lands in the same way it's launched. So that means it's launching from the edge, and when it lands, it's going to land on the edge. Now, if you decrease the height, no, that's not going to happen because the launch height has actually been decreased. So therefore, you're actually decreasing the time of flight, which would then actually decrease the range. So the poor the cyclist will actually hit the side of the ramp. It won't actually land on the curved part. Explain, so we've got a ball that's been launched. Explain why air resistance decreases the horizontal component. So we're looking at it this way. So the horizontal velocity is traveling and it's going to be colliding with air, so therefore that's going to experience a force. And if it experiences force opposites to its motion, it will undergo deceleration. So therefore the magnitude will actually decrease, so its range would also decrease. On the diagram, draw the path of the ball when it's launched, then present there, same velocity, same height, okay? Now there's also air resistance in the vertical component as it's going up, so therefore the maximum height will actually be decreased. So these are the two key features that you need to have in your diagram. The maximum height, or the zenith, will be lower, and the range will also be decreased. So as long as you've got a diagram that shows those two factors, you don't need to get any more technical than that. Now explain why it doesn't reach the maximum height. Okay, so it actually decreases. The air resistance and the force due to gravity is actually adding on to the deceleration on the vertical plane. So therefore the rate of deceleration is going to be higher than 9.8. And that's it.